In this video, I'm going to derive the temperature and pressure correction using the ideal gas loss. So let's do that. So remember, when you have an ion chamber, I'm going to draw an ion chamber here. It's got a center electrode, and there's all kinds of gas molecules in here. This is open to the atmosphere, so as the temperature and pressure change, the number of gas molecules inside here is going to change, and the charge collected will change. More gas, more charge for the exact same number of x-rays, less gas, less charge for the exact same number of x-rays. So we have to correct for that if we're going to do beam calibration. So we got to use the ideal gas law. So remember, ideal gas law is pressure and volume multiplied together equals number of gas molecules inside of this, constant R, and the temperature T. PV equals nRT. We need to take the conditions here and convert them to the standard temperature and pressure that we use for beam calibration. So I'm going to just do it generally here. PV1 multiplied by N1, R, and T1. That's maybe like one set of conditions and then a different set. P2, V2 equals N2, R, T2. And we want to solve this. So in this situation, the volume inside this chamber is constant. V1 equals V2. So we can set these two equal. We can have V1 equals N1 R T1 divided by pressure 1. V2 equals N2 R T2 divided by pressure 2. These two things are equal, so I'm going to get N1 R T1 divided by P1 equals N2 R T2 divided by pressure 2. These R's can cancel out. We can get rid of that R now. If we're trying to correct a reading at pressure 1, volume 1 to pressure 2, volume 2, we basically need to know the number of gas molecules. So it's driven by the number of gas molecules. So I'm going to solve this for, like, let's say N2. So N2 is equal to N1 T1 divided by P1. And then this one flips, so pressure 2 divided by N. Oops, the N doesn't go there. Pressure 2 T2, the N2 stays over here. Now this is number of gas molecules, right? It's not charge collected by this chamber, but like I said before, the charge collected for 1 is proportional to the number of gas molecules, and the charge collected by condition 2 is proportional to the number of gas molecules in that condition. So what I can do is take the ratio of these two things. So charge 1 divided by charge 2 is equal to N1 divided by N2. If I want to slip, let's say like I'm going to slip it in there, so I need to know that N1 is equal to charge 1 over charge 2 divided by N2. I did that wrong. Multiplied by N2. So I get N2 is equal to N2, charge 1 over charge 2, temperature 1, pressure 2, temperature 2. So N2 is going to cross out, and we're going to take C2 and bring it up here. Charge 2 is equal to charge 1, temperature 1 over pressure 1, pressure 2 divided by temperature 2. And the calibration conditions that we use, like for the NIST calibrated chambers, are that temperature is equal to 22 degrees. They use this one. This is not standard temperature and pressure. Standard temperature and pressure is 0 Celsius. 22 degrees is like a typical room temperature. And then the pressure they use is 760 millimeters of mercury. Temperature of 22 degrees is equal to, we have to use Kelvin, so it's equal to 295.15 Kelvin, degrees Kelvin. So we're going to slip this in here. We're going to call that P1. So let me move that up. Charge 2 is equal to charge 1. T1 is going to be temperature at the time of treatment, so it's going to be T1 divided by T2, which is 295.15 degrees Kelvin. Pressure 2 is just going to be the